Okay, let's have a look at the question here. So we want to prove that 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed up until the general formula of n times 2 to the power of n equals to the right-hand side of n minus 1 times 2 to the power of n plus 1 plus 2. So you can see that initially looking at it, it does look quite complicated, but don't be put off by that. Okay, we just want to go follow the same steps that we learnt before. Don't be put off by how complicated the equation looks. So remember, the first step is to show that it's true for the initial value. And to do that, we need to work out what the initial value of n is. And by looking at the general formula here, and also the first term, 1 times 2, you can see that n must equal to 1, to have 1 times 2 to the power of 1. So therefore we want to show that it's true for n equals to 1. And how we do that is by considering the left-hand side first. So let's look at the left-hand side. And using the general formula, we have n equals to 1, substitute that in, 1 times 2 equals to 2. And now the right-hand side, just substituting 1 into this formula, 1 minus 1 just gives us 0 for all of that, and then plus 2 equals 2. So now we have shown that the left-hand side equals to the right-hand side, and therefore this is true for n equals to 1. Okay, so we've done step 1, we've shown it's true for the initial value of n. Now up to step 2, where we want to make the assumption. So remember how I said we must write the word assume, yeah? That it's true for n equals to k. So that is, we want to prove that it's true for whenever n equals to k, that the left-hand side equals to right-hand side. So we're making the assumption that this does equal to this, yeah? And why we do that is so we can use it in step 3. So once we've written this all out, so I want you to write this out completely like this, okay, before we move on to step 3. Now in step 3 is when we want to show that it is true for n equals to k plus 1. That is that this left-hand side equals to the right-hand side. And remember, to get the equation for this, what we do is we add the next value onto this series over here. So we just substitute k plus 1 into this formula. So instead of n, we have k plus 1. And instead of 2 to the power of n, we have 2 to the power of k plus 1. So this is our additional value. Now on this side, what I've done is substituting k plus 1 into here. We have 1 minus 1, so that just leaves us with k. Can you see that? And then here we have k plus 1 plus 1. That's why we have k plus 2. And that's how we form this equation. And remember, what we're trying to do is show left-hand side equals to the right-hand side. So keeping that in mind, we start with the left-hand side, which equals this. And the step we do now, good, is we need to use the assumption that we made in step 2 and substitute it in. So let's identify which part of this left-hand side looks like the assumption. And that's going to be this part, isn't it? Because that's before we added in the extra value. So instead of writing that, I'm just going to substitute in this into here. Okay, so I've just substituted this in. So we have k minus 1 times 2k plus 1 plus 2, right? And so remember how I told you, always keep your eye out. This is what I want it to look like, okay? So always keep that in mind. So now we've substituted in. We think to ourselves, well, I think the best thing to do here would be to factorize out the common value, wouldn't it? So then we have the 2 to the power of something, just one of them, rather than 2 separate values. So that plus 2, we've just isolated out to the back, and we're just considering this term here and this term here, and we've factorized out 2k plus 1, right? And that leaves us with k minus 1 plus k plus 1, okay? And now I'm just going to summarize this. So k plus k gives you 2k, minus 1 plus 1, just 0. So that's why it becomes 2k times 2 to the power of k plus 1 plus 2. Okay, let's look back to the right hand side. So here we have the plus 2. Okay, so that we have, but what we don't have is the k times 2 to the power of k plus 2. We have k to the 2 to the power of k plus 1. So how am I going to change that so we get the k plus 2? Well, you can see that we have that 2 there, right? So I want you to consider it as k times 2 times 2 to the power of k plus 1, right? So this is 2 to the power of 1. So if I put this together, this is going to give me k times 2 to the power of k plus 1 plus 1. And that's how I get 2 to the power of k plus 2. Okay, can you see that? How I'm using this 2 and adding the indices together to give me the 2 to the power of k plus 2 that I need. And now you can say that yes, that does look exactly like the right hand side. So I've shown that the left hand side equals to the right hand side. So I can say that therefore I have proven that this is true for n equals to k plus 1, because I've proven that for n equals to k plus 1, the left hand side does indeed equal to the right hand side. So now we need our conclusion, which is therefore the formula. So in your exam you would prefer to write this out in full. So therefore this is true for all integers of n is greater or equal to 1. So remember how I taught you to always check, was the initial value n equals to 1? Yes? Good.